stability of the film, whether it is stable along against the thermal stress and humidity or not. So you have to repeat the XRD measurement after exposing the film to high temperature for some duration. For instance, here we have done this test for 60 hours exposure to the high temperature like 90 degrees C, and you have to repeat the absorption spectra. We have done it after the exposure of the film to for 40 days, and this is the Tga analysis where you can you can see whether the material any weight loss is occurring when you are applying some high temperature or not. So this is about the stability. Okay, your film is made, you have studied you have characterized it, you have checked its crystallinity and surface feature, then you have checked the stability. Now, how to utilize this film? This is the important part. You have to utilize this film for some sort of devices, and these applications include solar cell, transistor, memory device, photodetector, light emitting diodes, and laser. These three, I have changed the color of these three because I have personally worked on this, and especially on the solar cells. So I would like to briefly explain how to fabricate these devices from the fabricated film. Here you can see this is the device structure. For solar cell device, you need substrate, electron transporting layer, which is indeed an N-type material, then active perovskite layer, and after that a P-type material or hole transporting layer, and then the electrode. So here you can see, but these things are carefully to be chosen because of the energy difference. If there is a larger energy difference between the electron transporting layer and the active perovskite layer, then it will be very difficult for the holes or the electrons to move toward the respective electrode. So you must have to choose the material which has minimum energy band offset with the active material, so that you can get a very smooth charge transportation. Okay, and when you have made the device, then it comes about the characterization of the device. So here this is the cross-sectional SEM image with false colors. It is indeed this architecture which can be seen through the SEM after you make the real device. And from this we are usually calculating the thickness of each layer, and then you have to calculate the current density and voltage profile. For this you guys have to use the solar cell simulator, and this simulator will calculate directly all these properties. Otherwise you can also calculate these characteristics from this graph, like the fill factor, open circuit voltage, short current density, and the most important is the power conversion efficiency of the cell. The next characterization, you can calculate electroluminescence quantum yield, and also you can calculate the current density here, and then you can compare the current density with the calculated by the solar cell simulator. And one other thing that can be done is the dark voltage characteristic. In the previous one, when you have a solar cell device, you have to throw light on it and it will produce current. Okay, but if you apply current to the device, then it will give some characteristic which are known as SLC characteristic or dark current voltage characteristic. These characteristics are usually got three regions, like linear region and J proportional to n greater than 3 and J proportional to V square. So from these regions, you just need to figure out that from where this region, Trafford region is started. So you have to note this point and check the voltage of this point, then use the voltage here in this formula, the thickness of the film, and directly you will calculate the number of traps inside the material, mean where the charge carrier may be trapped to produce some non-radiative transition. So the smaller this number, the better is the material for the solar cell. Okay, and then at the end you can check the stability of the film. You have to repeat these measurements again and again for extended period of time. So this is nothing but the repetition of that. It is just to check the stability of your device. Okay, after this you can also utilize this material for the resistive memory devices. This device is very simple, but I don't know whether here you have the characterization tools for this or not, but the device fabrication is very simple. You have to just deposit the perovskite film on the ITO glass, and then you have to deposit some gold electrodes. This process is a bit intricate, but we have tried even a gold wire for this. So you can use here just a gold wire which is touching this surface. So you need gold wire, ITO substrate, and just the precursor solution, and you can make this device. And if you want to study the characteristic of that, so you can see here that I didn't define it. Actually, ReRAM device is when you are changing the resistance of the material, so it stores the data on that principle. Mean changing the resistance can provide the storage of the data, just like that magnetic hysteresis loop. But here the things are electrical, not magnetic. So if you change the resistance to here, just like the hysteresis loop, and then go back, so there comes some area, and this area defines how much data can be stored here. And after this, you can also utilize the same perovskite material for field effect transistors. This device is also very simple. There is no sophisticated layers, just the silicon dioxide wafer and perovskite film, and then 2 electrodes. But the most important thing in this device is the distance between the 2 electrodes. This distance must be lesser than 20 microns, otherwise the electron in hole will not be able to reach the respective electrodes. Here in our lab we have utilized the lithography techniques, where we have separated one perovskite, small sheet of 2D perovskite, and then we have fabricated the gold electrodes upon it. And the characterization of this device, you just have to measure these 2 things, because the FAT characteristics are, if you change the gate the gate voltage, then the current, the drain to source current will be controlled by changing this voltage. So if you look here, if we are changing the gate voltage, then we are getting different current voltage characteristics. Okay, so this part of the talk is most important, because if somebody wants to start their work in the field of perovskite, so you must have to look here for the opportunities. So the uppermost thing is the environmental stability of the perovskite material. So if somebody wants to start their work in this, then you have to think about some techniques or some other ways to increase the environmental stability of this material. Then the toxicity and these interfacial engineering, also new material and fabrication of the new methods. So I'm going to explain them one by one, and explain also that how can you start your work in the field of organometal-halide perovskite. Here you can see actually the perovskite material is extremely unstable in the ambient environment. Let's suppose there is a little bit humidity in the environment, then it will interact with the perovskite material and it will be decomposed into its constituent, and the material will be no more a perovskite. But you can see here, this blackish film is as prepared film, and after the exposure to ambient air, you can see here all the species are just flee away, and only the PBI2, which has a yellow color, is left in the film. And you can see the efficiency of the film. The device, it was about 12, so it reaches to this, and when it was 8, so it reached to this. So it means just in 19 days the efficiency of the device is reached to about 50% of its initial PCE. At the other side, if you are considering the silicon-based solar cell, so it guarantees about 25 years of operation without any loss in the power conversion efficiency. So it's far away from the commercialization. So you have to think about some strategies how to increase its environmental stability. This is this diagram is actually from our work, and we have mentioned some strategies that how you can increase the stability of the perovskite material. The first one is this encapsulation, and I think luckily we got this. Sir Nasir Ali is working on this thing. They have utilized some simple glass material in which they have doped some metallic nanoparticles, and those nanoparticles are acting just like the energy converters. Like if there are high energy photons fall on it, it converts it into a lower energy, which are not only valuable for the increasing the efficiency of the device, but also they are converting the harsh UV light into the longer wavelength light, which is not disrupting the structure of the perovskite. Another is just put some layers, like somebody used single wall nanotubes upon the surface of this, which has greater conductivity and also greater resistivity to the environmental factors. Also, you can modify the surface, make the film, or just put something inside the perovskite material which can resist more to the environmental factor, especially for the humidity and light. And one other thing which I have personally worked this one is to utilize the two-dimensional perovskite with the conventional perovskite material and increase its stability. What is 2D perovskite? So I have shown in the very first slide that we got the perovskite structure, which is actually the combination of the octahedra separated by a bigger cation. So in this, if you convert this structure into 2D form, so you can see here. Now if you replace this cation with a bigger one like these, which are indicated by the arrows, so these octahedra will be separated from each other, and the perovskite will be converted into a layer form. So since these organic cations indicated by arrows are more hydrophobic than the these cations like Fa or Ma or CCM, so they are increasing the environmental stability of the material. So in our work we have combined the 2D perovskite with the 3D perovskite, and we get some result like this. Here, this is the famous or the typical absorption slope of the perovskite, but here you can observe some small bumps as well. It means these small bumps are arise from the 2D perovskite, and this is from the major 3D perovskite. We also observed that the band gap can be changed with the increasing concentration of some molecular or 2D material, and also the PL spectra is changing. Not only the intensity is increasing, but also the PL peak is shifting towards the higher energy, and the existence of the 2D perovskite can be confirmed just by using the FTIR measurement. Besides this, if you want to check the stability, because our purpose was to increase the stability of the perovskite film, so we have conducted the contact angle test. Mean we put in a drop of water on the different perovskite material, in which we have added 2D perovskite, and which is pristine, or there is no 2D perovskite material added. So here you can see the water can easily spread upon it. It means the water is absorbed more as compared to these material. If we are increasing the concentration of the 2D material, so the contact angle is increasing. It means the hydrophobicity of the material is indeed increased. Also, we have treated it for high temperature and then measured the XRD, so the XRD peak didn't change. We also measured the absorption spectra again and again for more than 50 days. It also didn't change. We also observed we also measured the Tga measurement, and here you can see that up to 100 degrees C or 150 degrees C there is no weight loss in the material. It means the material is pretty stable for the temperature about 200 degrees C. Okay, and another thing, this was one of the opportunities that you have to think about some strategies that can increase the stability of the perovskite material. The second is, which is nowadays a very big hurdle in the way of the commercialization of this brand new material, is the existence of the lead. Lead is very toxic to human environment, and the scientific community are thinking to find some alternative to lead. So you have a lot of options. You can see here in the periodic table, you can use all of these material as a lead replacement, but you are not going to move towards these because they are even more lethal than the lead. And if we have studied some up to electronic properties of this material, and we have filtered that these materials are more suitable to be utilized instead of lead due to their comparable properties with the lead. And indeed, we have chosen the bismuth from this. We chosen lead, bismuth is a replacement of lead, and the reason is their cost, their cost is lower than that of lead, and they are more stable in the ambient environment. They are non-toxic, they have comparable absorption properties and other optoelectronic properties, but there is one problem with this material. Their PCE is extremely low. It's about 1% only, but at the other side, all the things are in the favor of this, but one thing that is standing tall is the PCE of the lead-based perovskite material. It is about 25%, so 1 to 25, it's a huge difference. And the main reason is, there are several reasons, but one of the reasons is the bad film morphology of the bismuth-based perovskite. When we are fabricating the bismuth-based perovskite, then it is highly volatile as compared to the lead-based perovskite. So during the spin coating, the crystallization process is so quick that separate phases are formed, and one is unable to obtain high quality bismuth-based film. So we tried to solve this issue by utilizing that 2D perovskite material to this bismuth-based perovskite, and we have observed so many changes, not only in the surface morphology but also in their crystallinity and their other optoelectronic property. Here you can see this is just a simple, or you can say a pristine bismuth-based perovskite film. So, if you see here, it is not even a film, but some larger sheets on the substrate. But when we have added this long chain or long organic material into the bismuth-based perovskite material, a small volume portion, like you can see here, this is 2%, 4%, and 8% of the volume fraction. So you can observe the change in the film morphology. Here it is converted into some grains, then the holes in between, or the pinhole in between the grains is decreased, and at last you can see here we got a smooth and highly compact perovskite film. And you can see here the surface roughness of the film is also decreased, and this is the evolution of the film. You can see here it converted from sheets to the nanoparticles, and you can also see the contact angle. Again, the contact angle is increasing, it means the porosity of the film is decreasing. We also observed some more changes in the optoelectronic properties, like, and here the crystallinity is also measured. So you can see here the XRD spectrum shows that almost there are no peaks, mean the peaks are very faint, which indicates the poor crystallinity of the material. But here at optimum concentration, mean 8% of the organic material into the bismuth-based perovskite, the crystallinity is increasing, also the crystal became more oriented. And if you see here the absorption spectra, then the absorption spectra is getting more steeper and steeper. Steeper absorption spectra mean less defect concentration, so it means the defect concentration are also decreasing, and when the defects are less, so the material shows better photoluminescence property, and also the TRPL, or the lifetime of the carriers, is also increased because the trap centers are decreasing. And this is the lifetime, the increasing lifetime with the increasing concentration of the 2D material. And also we have utilized Raman spectroscopy to study the crystallinity of the material. And we directly measure the defect concentration of the material. So in the very first slide we have discussed about the trap field center voltage, which is directly proportional to the number of traps. So you can see here the trap field limited voltage is about 2.54, but here it is decreased to 1.22, so it means the trap sizes are also decreased. And finally we fabricated the solar cell device, which exhibited a larger improvement in the device performance. Like you can see here, the PCE was for the pure bismuth-based perovskite based device was about 0.6, but we got an improvement up to 1.308%. And this we just looked for the literature, and we got that this is the highest PCE which is reported for the any bismuth-based perovskite. And another thing, after the toxicity,